Okay, here we go. So we're going to try and explain this particle system from bottom up. So normally when we look at our class diagrams like we see here, typically we want to start at the end of the chain because all the other ones above it require that one. So for example, particle doesn't require anything to exist. However, emitter requires particles. We have to create the particle before we can create the emitters. And the main requires the emitter. So and the chain goes on. So we're going to start at the bottom of the chain, which is particle, and then we're going to work our way up to emitter, and then we're going to tie everything together in the driving class, which is the main class. So let's start off with the particle. And I'm going to try and explain this in as much detail as I possibly can, but remember that this code will be available to you on the class website. And of course, you're watching as I go on, so you could always pause the video and do whatever it is you need to do to get everything you need. So I want to break this up, and again I want to emphasize that basically a particle is nothing more than the projectile demo that we did previously. So as you can see here, I've actually separated the data. Here's all the old projectile data, with the exception of 4 additions, which I told you about during the previous video, is some duplicate data for recording the initial transparency, the initial position, initial trajectory, and the initial opposition forces. And this is for the reason why we have this is to recycle our particles and reset them after every time their life expires. Other than that, it's just all the same basic data that every other projectile has had since we started talking about them. The particle data, as you can see, very limited, only the lifespan. Now I want to emphasize this one thing, that the particle system that we're displaying here is a very simplified version. You can make much more complex versions that start to add in a whole lot of other effects and whatnot, but we're going to keep it simple and just do the basics, and you can apply it and add to it as you need to for your particular program. So this is all the data we're going to need. So we have our forces that are going to apply, our gravity and our wind. We have our launch angle and our launch speed. We have our image data for our particle itself, whether it's active, I should say, sorry. Transparency, position, trajectory, and forces. Position, where is it currently located? Just the vector 2, so just the x and y location. And the reason why we're doing this as a vector 2 float is so we can actually record those partial pixels. And what will happen is those partial pixels, as they're cast to integers during the destination rectangle drawing, they will eventually average out, and you'll end up with a nice smooth motion as things move around the screen. Anyways, so and then as I mentioned before, this is just duplicate data. Wall collidable represents whether the particles should collide with the 4 walls of the screen, and of course that would require the screen bounds as well. I've given all the data some default data just because that's good style, but as you can see, once we get into the constructor of our constructor of our class here, it actually sets up this data manually. So let me just kind of readjust this so it's easier to read, so you can see everything all at once on the screen. So the first thing we're going to do is I've explained everything in the pre-post conditions, what each parameter represents. Now there's other data that's going to be calculated from this parameter, so all the data that exists up here is not necessarily parameters for the class. They're just, some of that is actually calculated, like the trajectory and the forces and whatnot. So let's take a quick look at it. So here's all the given data that we get from the parameters: the image, the gravity, the wind, the angle, the speed, the lifespan, transparency, and then I set the duplicate transparency as well as soon as I have it. Whether it's collidable, the screen bounds, all that information is set. We don't have to calculate anything. Now the start position is just a recording of the rectangle for the particle itself, so I've just recorded that for later on. Now the start trajectory and start forces, notice that I'm calling these 2 subprograms that we used in the projectile code before, Calc launch trajectory and Calc force vector. All Calc launch trajectory does is do some basic trigonometry, SOHCAHTOA, to calculate the x and y components of the particle based on its speed, which represents the hypotenuse of the triangle, and the angle that is being launched at. So then we get the x and y components of that using sine and cosine, and then that is going to be our trajectory, our vector of motion. The opposing forces, because I've limited things like gravity and wind, limited it to gravity and wind, gravity is always going to be our y opposing force, so it's always going to be pulling us down to the ground. And for this simplistic demo, wind is always going to be moving left or right. We haven't added any other directions on it, just to keep it simple. So wind is always going to represent our x component of our opposing forces, and gravity is always going to represent our y component of our opposing forces. And then I've just copied the data into those other vectors. These are the vectors that we're actually going to manipulate throughout the course of the life of the particle. These are the ones that we're going to call upon later on to recycle the particle back to its original state. So don't fret too much, but these are the position, trajectory, and forces are the ones we're going to manipulate as the particle is being a projectile. So the same update and draw logic is here as was in projectile. Nothing really has changed here. Just draw the sprite. Nothing special here. Update, basically this is the only change you're going to see. We add in the amount of time passed since the last time it's updated. If the life spent is more than the lifespan of the particle itself, we reset the particle. And then we return false, meaning the particle is now dead. The reason why we return that is the emitter needs to record which ones have died and which ones are still alive. That way it can keep track whether the emitter itself is complete its work. Because remember, some emitters aren't infinite cycling. Some actually stop as soon as it's all of the particles. So we need to return that data back. However, if the particle is not dead, it's going to return true, saying, "Hey, I'm still alive." You'll notice down after lifespan, if this returns here, none of the work below is done because the return statement says, "I'm all done this subprogram. I'm all done. Go away." However, if that's not the case, we continue on and we update the projectile position. Now, I'll come back to this in a second. That basically moves it along its path, taking into account its trajectory and the opposing forces. This wall collidable, if we are supposed to be colliding, then check our collisions with the four walls, and if we collide with any one of the four walls, reverse its motion with that wall. So for example, if I collide with the left or the right wall, I'm going to invert the x trajectory, or the x component of the trajectory. If I collide with the top wall or the floor, I'm going to reverse the y trajectory. I've added a little bit more to this just to try and give it a sense of realism, where I've actually reduced the y velocity if we interact with the floor to simulate it bouncing off the ground. That's just to slow things down and make sure that the program looks a little bit more natural. But you don't have to do that. That's up to you. You could also do the same thing on the other walls as well to simulate the idea of the bounce absorbing some of the energy of the projectile, the kinetic energy of the projectile. So now the draw, as I said, is just drawing the stuff. Is active. This can be used outside by other things like the emitter or whatnot to check to see whether a given particle is active or not, and that way it could know whether it wants to affect it or just leave it alone. Set transparency. This, I want to note that I've bounded it between 0 and 1, which means it'll never get more than 1, it'll never get less than 0. And I just did this by a couple calls to math.min and math.max to keep it into that boundary. You could break that down into separate calls, but why when it's very simple? And then I've also taken that transparency that we just calculated it, and then we applied it to the image itself. So when it does the draw command of that sprite sheet, it actually takes that into consideration. Get transparency just returns the transparency, nothing special there. Get lifespan returns the total life of the particle, whereas get life spent returns how much of the life has been used up. Now, why do you care about this? Well, because if you do a little simple division, you could see how much of the life has been used up. So life spent divided by lifespan could result in, let's say, for example, a 0.7, which means 70% of the life is used up. You could then take this information and start doing some interesting things like modifying its transparency. So basically you could make the particle fade out as it got closer to the end of its lifespan, very simply by just doing like 1 minus life left, which is a really cool little effect. So anyways, Launch actually will launch the individual particle. And all it really does here, it says, hey, if you're not yet launched, launch. Set its active to true. If there is more than one frame in the sprite sheet, start it animating. And then return true, saying that we successfully launched. If for some reason we didn't launch, meaning it's already active, then just return false, saying, no, you just tried to launch something that was already launched. Don't quit wasting my time. Reset particle does exactly that. It takes all the trajectories and positions and everything like that and sets them back to those starting values. And it also resets the destination rectangle for the image as well, so it's consistent with the position. It resets the life spent back to 0, and it resets the transparency back to its original transparency. And it deactivates the particle, so it will no longer be updated, and it will no longer be drawn. If the image is currently animating, then stop the animation. We don't want to waste the CPU cycles of it animating if we don't have to. That's just a waste of time. And then we get down to the calls that I was already mentioning before. Calc launch trajectory. This is where the sine and cosine, the trigonometry, comes into play to get the x and y components of our movement. And the set force vector, again, just takes the wind and the gravity and applies them as the x and y components of our opposing forces. Update projectile. This is where all the magic happens, but you've already seen this before. There is literally nothing different here. I've just said, let's take in how much time has passed, and we factor that in to scale our forces to make sure that we're applying the amount of force required for the total amount of time passed. So it's not a full second that passes, it's a small fraction of a second. So we don't want to apply 1 full second worth of opposing forces. We want to apply however much is passed. So that gets applied to the trajectory on a permanent basis, as before. And then that trajectory is then applied to the current position. Again, we factor in the time. And then finally we apply the new position, which is a very accurate position, taking into consideration partial pixels and whatnot. And we cast that to an integer to only get full pixels, and put that into the image itself. And then the collision detection, this is a very straightforward thing. I just detect whether it's exceeded any one of the walls, right, left, up, and down, and if it does, we just reverse the trajectory and we move it back so it's in line. Now you'll notice that for this one right here, for the floor, I've actually not only did I reverse the trajectory, but I also scaled the trajectory by a value of 0.2 to 0.4, a random value of 0.2 to 0.4. So what that does is it scales it and reduces it by 20 to 40%. Actually, sorry, the inverse of that, by 60 to 80%. And what happens is it'll make the ball bounce less. Otherwise, it would look like it's getting the exact same bounce every time it hits the ground, and that could look a little awkward. And then just the top, right, left wall, the exact same stuff, inverse the trajectory and reset it so it's not exceeding the boundaries of the wall. And then finally, I have this other handy-dandy little functionality that the emitter may commonly use to re-randomize the trajectory. So it'll re-randomize the speed and the angle between its ranges, like its low range speed and its high range speed. Same with the angle, and that way it'll calculate a brand new trajectory. So what'll happen is when the particle recycles, when it resets itself, it won't go in the exact same path it did last time. Otherwise, you'll start to see, if you watch it, if you only have a few particles, you would actually see a pattern if it always went on the same trajectory, and it wouldn't look very chaotic, it wouldn't look very natural. So this actually creates that chaos, and that is an option. You don't have to call randomized trajectory. That is totally up to you. You can customize these things however you see fit. If you want it to be consistent, hey, make it consistent. It's up to you. You're the boss. So that's it for particle. The next video we're going to talk about emitter, which should be a much shorter discussion. But this is the biggest one, the most important one, and that's the particle itself. But remember, it's nothing more than a projectile.